Morning. I'm Hosho Katsura, the chair of this session, so let's get started. And the first talk of this session is the last lecture by the review on Calogero model by Alexios Polychronakos. So yeah, please start.
Thank you. Thank you. Thank you for being here this morning. My voice had a trip to nothingness during the weekend, but today it's good. So as long as I don't talk too loud, it will be fine. So today we're going to conclude our trip to Calogero system. We will finish with our treatment of the particle system, and we will show how we can distill from the particle system spin chain models. And then we will proceed to the large N fluid mechanical description and make contacts with previous talks, especially by Sasha Abanov on fluid mechanics in the Calogero model. So I just, as a review, I just remind you that last time we left it, that using this exchange operator or exchange Calogero model and restricting ourselves to purely bosonic or fermionic states of particles with internal degrees of freedom, for free, without any extra work, we ended up with a model where the particles have also spin. This sigma ij is the spin exchange operator, and by spin, I remind you that what I mean is an SUQ degrees of freedom in the fundamental representation. So it doesn't have to be spin half SU2, can be SUQ, but it has to be in the fundamental representation. And the two signs here, ferromagnetic, anti-ferromagnetic, have to do with looking at bosonic or fermionic states of the full model. This coefficient L is arbitrary in this formulation. It has nothing to do with any group theory or anything else. And therefore, it can be taken to have any value, which will be important. And specifically for the value L equal 1, this model is one of the models that we also derived from the matrix formulation when there the fundamental or the anti-fundamental realization of the angular momentum was chosen. But that's not going to be too important for us. I will very briefly mention, not even describe, I guess, that by using the fact that this started as an integrable model, that means that it's also solvable. And you can find the spectrum and the eigenstates of this model with the particles having these spins, and you can do it through these operators. But the lesson to draw from here, which we will see more explicitly in what comes, is that the spectrum is very similar to the spectrum of free particles with its internal degrees of freedom. It's just that the energies are renormalized for the Calogero model, which means shifted for the harmonic Calogero model, or renormalized in a rather different way for the Sutherland, the periodic model. But, and here I state how the wave functions actually look. The ground state wave function is always of that form. There is a harmonic factor. There is this famous van der Monde in the 11th power, and then some totally symmetric spin state, or some totally anti-symmetric spin state if you're talking about the anti-ferromagnetic model. And the degeneracies are exactly as you would expect if those were free. By free, I mean non-interacting particles. Of course, the treatment that I gave you before is well suited to find the spectrum and eigenstates of the harmonic model. That means inverse square interaction in a harmonic trap. And these wave functions do refer to that model. But what about the Sutherland model with spins? They are finding this spectrum is a little bit more difficult because we don't have commuting operators anymore. We have these operators that do not commute, but they are fully symmetrized sums of powers commute. And there, better call a different method, better call the asymptotic bethe ansatz. So, you're probably familiar a little bit with the asymptotic bethe ansatz approach. It's an approach that is well suited to integrable systems, of course, especially when the particles have to obey periodic boundary conditions, because it allows you to calculate the states, the energy eigenstates and eigenvalues rather, of the model, simply using as input simply the two-body scattering matrix or amplitude. So this is a very good approach and a very physically motivated approach to use in our problem, especially keeping in mind that Calogero particles are somehow like free particles obeying fractional statistics, fractional exchange statistics, which is encoded in their scattering matrix. And this treatment will be based on one key fact, sometimes I call it an amazing fact, and that answers a little bit the question that you asked me last time, that we stressed that Calogero particles cannot go through each other because the inverse square interaction is just too strong and there is no tunneling. And therefore, the real statistics of the particles are irrelevant because once you start with a sector, you stay with that sector. There is no interference with other permutation sectors. Statistics don't matter. In fact, the situation is completely inverted when you consider the exchange Calogero model. That means the Calogero model where the strength of the interaction is not L times L minus 1, but L times L minus this Mij. Forget H bar for a moment. It turns out that in that case, not only can particles penetrate, but they have full and perfect penetration. If I start with two Calogero particles interacting with this Calogero exchange Hamiltonian and they scatter, eventually they go through each other without any backscattering at all. This is quite surprising and unusual. The way it happens, of course, is that the Hamiltonian, other than the standard 1 over x squared interaction, which is integrable, contains this term that teleports the wave function from one side to the other. It's like beam me up Scotty type of interaction, for those of you of age to remember the old Star Trek. But, and the two combine and conspire in exactly the right way to have full penetration. There is a quick and easy proof. This is a much more general statement, but there is a quick and easy proof for the harmonic scattering Calogero model. We have these pi i's, this operator pi i's that are all commuting. So you can definitely build up eigenstates, simultaneous eigenstates of all these pi i's for distinguishable particles. These eigenstates asymptotically, when the particle coordinates are far away from each other, become eigenstates of the momentum because the pi's are the momenta plus some inverse square exchange terms. And therefore, such eigenstates are eigenstates of the momenta no matter where the particles are. So to have backscattering, you must have that the momentum is P1, P1 and Pi1, sorry, P1 and P2 when particle 1 is to the left of particle 2, and the opposite when they scatter when particles are in the other way around, to have backscattering. If this is an eigenstate of the momentum of individual particles for all asymptotic regions, it means that there is no backscattering. And here I give you a puzzle, kind of like a take-home puzzle or exercise. What about the correspondence principle, the classical limit, h bar going to 0? If I restore h bars in my description, h bar would go here. Remember that L times L minus 1 was kind of a quantum correction to L squared, and when I put all the h bars, this becomes L times L minus h bar Mij. So when I take h bar to 0, this term drops. However, for any finite value of h bar, this system has full penetration. So how can I have full penetration at the classical limit? At the classical limit, there is an inverse square potential, and particles will go there, stall, and come back no matter what energy they have. Think about it for a while. Tell me individually if you have found an explanation. This is not the only instance in which the naive correspondence principle fails. There are more elementary ones that we teach sometimes in quantum mechanics courses, but this is a particularly interesting one. For Calogero particles, the Yang-Baxter equation is trivially satisfied. I remind you that the Yang-Baxter consistency equation is that when you have a three-particle scattering, and you want to claim that this three-particle scattering can be written as a product of two-particle scatterings, the order in which the particle scatters should not matter. Otherwise, it wouldn't be consistent. Here, there is no issue. We don't even need to check anything because particles simply go through each other. So which one went through the other one first or second, it doesn't matter at all. The scattering matrix is completely trivial. It's one, so it satisfies this relation. And of course, the total scattering phase will be the sum of the individual two-body scattering phases. Again, that famous factor. I think this is a good going to have a small sidebar on the Yang-Baxter equation, since it is applicable beyond the Calogero model. The fact that particles go through each other means, as I said, that this equation, which is the Yang-Baxter equation, is trivially satisfied. Now we are used to thinking that the Yang-Baxter situation is paramount for integrability, and in fact it is a hallmark of integrability. If you see it, then you have an integrable system. Actually, I would like to stress that it is a necessary but not sufficient condition for integrability. And also to give you the mental picture that what the Yang-Baxter equation is, in words, is the absence of Aharonov bomb effects around triple scattering points, triple coincident points. Let me expand a little bit on that on the blackboard. Assume that you have a scattering of 3 particles. The center of mass trivially factors, so you can write your wave function as a center of mass wave function times the relative wave function, and you can choose as relative coordinates what you want. You can choose x1 minus x2 and x1 minus x3. You can call that y1 and y2. So let's plot these 2 variables. Let's put x1 minus x2 here and x1 minus x3 here. As the particles scatter, some of these particles, the 3 particles scatter, some of these particles will go over each other. That means in the configuration space, there's a point in which they coincide. You see that if particle 1 and 2 are together, y1 is 0. So this axis here represents particles 1 and 2 coinciding. When particle 1 and 3 are at the same point, y2 is 0. So this axis here represents particle 1 and 3 being on top of each other. Finally, when particles 2 and 3 are at the same point, these 2 variables are equal. So this diagonal here, y1 equal 2, represents particles, the configuration points for which 2 is 3. Now assume that you have an interaction that is either local or asymptotically falls off to 0 as the particles fly away from each other. So you could start from one of these 6 now domains in your configuration, 6, the same number as the number of permutations of particles. Each one of those domains represents an ordering of the coordinates. You can start from a domain like that asymptotically and write a plane wave. I will do it like that. That means you write a plane wave in these variables, that the plane wave moves in that direction, so the particles are coming together. What is going to happen? Assume that you are interested to see what happens when particles 2 and 3 come together. Clearly, that represents scattering of particles 2 and 3 with particle 1 not participating, it's still far away. So if you know the incident wave here, let's call this region 1, you can deduce the transmitted wave on the other side. In going from 1 to 2, it's not quite the scattering matrix, it's what we would call the transfer matrix that is relevant to take the wave function from one to another region, but they are closely related. Once you have the wave function here, what plane waves you have here, you say that when particles 1 and 2 come together, then that wave function will have a specific value to that region. And finally, when that wave function is applied to this, you will have the wave function at this region. What I'm saying is that if you know what is your scattering asymptotic state here, by following these boundaries, you can deduce what it is here. On the other hand, there's another boundary here, and this asymptotic plane wave will hit it. So you know what the wave function, if you know the wave function here, you know what the wave function will be here. Let's call this for 6. Okay. Now in this wave function, again through the transfer matrix, you know what it is here, which is 5. And finally, through that scattering, you know what the wave function will be here. So you see that you have this excursion of the wave function going this way and that way. And by consistency, that wave function here should be the same whether you scatter this way or that way around that triple point. That's essentially what the Aronoff-Bohm effect is. In the abelian cases, you have a flux tube. If you go around one way or the other way, the wave function that you end up with has different phases. Here, if you do it one way or the other way around the triple point, the state, the wave function that you end up with will not have just different phases, but maybe different combinations of plane waves. For that not to happen, you need the Yang-Baxter equation. So this is just a mental picture, but it's kind of useful. It also reveals that what you have here is certainly necessary to have plane waves as asymptotic solutions, because what would happen if that were not true? You would need to add extra waves here, so eventually the full scattering state would not be a finite combination of plane waves, it would add up to something with many other waves, so you would have a most general scattering. But also this takes care only the coincidence points of two particles. What about the region in the middle? Just because the scattering through the boundary of particles 2 and 3 and so on and so forth works fine, it doesn't mean that this region here will not produce extra scattering that may spoil integrability. Integrability will be a consequence, where am I? Integrability will be a consequence of the Yang-Baxter equation. Only these triple interaction points are dynamically of measure zero. They are, of course, a measure zero part of the configuration space, but because your interactions may be finite range, the dynamical effect of those regions has to be insignificant or of measure zero. When does that happen? It happens when the interactions are purely local, say delta functions, like in the Lieb-Leiniger gas, or in lattice models where triple points don't exist actually, because triple points are not part of your configuration space. And in those cases, indeed, like the Heisenberg chain, and in those cases indeed, we have integrability because of Yang-Baxter. In our case, because this is a 1 over x squared interaction, triple coincident points do matter. There is a finite effect, so we should worry whether they spoil integrability. There are examples of situations where the Yang-Baxter equation is satisfied and the system is not integrable. And I can give you one in private. Luckily, we are in Calogero land, where everything is fair. So, because the Calogero model is integrable, we know that the Yang-Baxter equation will be satisfied, and it is enough, or we don't need to worry about anything else. So let's return to yes.
I understand the statement that the Yang-Baxter equation is necessary but not sufficient condition for the integrability. I think it's the other way around, right? It's sufficient but not necessary.
Absolutely not. It is necessary but not sufficient. It is necessary because if it's not satisfied, the superposition of scattering from the left or the right side from triple coincidence points will not produce the same wave function. So you need to keep adding, and therefore you will have dispersive scattering, I insist. It is not sufficient because the scattering of the point in the middle may be also relevant and important that will spoil integrability. And I have an explicit example where the Yang-Baxter equation is satisfied and the system is not integrable exactly because of this. I didn't mean to be curt there. I just wanted to stress the point because I know that sometimes it's the other way around. You say, oh, if I have the Yang-Baxter equation, I have an integrable model. It's not quite like that. You have to check. Integrability for models with either spin or particle degrees of freedom for me means that scattering momenta are preserved. There may be scattering, but the outgoing state will be a combination of superpositions of the incoming momenta, as opposed to a continuous superposition of all the momenta, because you have conserved quantities. But let's discuss a little bit, and then I'll show you what I mean. Absolutely. Right.
exactly right.
Exactly.
I think what our chairman is talking about is actually the Yang-Baxter equation for an R matrix. And if you have that, you can construct an integrable
Right.
model.
If you have an R matrix, then these are the bones to construct. Yeah, I
So
agree.
I think it's just, you're looking at different objects.
Absolutely. May very well be the case, yes. Okay, good. So for the Calogero model, where we know that the Yang-Baxter equation is valid and two-body scattering is actually enough to find the n-body scattering, we can apply the asymptotic bethe ansatz, which means the following. If your particles live in a periodic space, you can simply assume for a moment that there are asymptotic states like that. When the particles go over each other, that means when you follow the wave function, when the particles jump over each other, you have to consider the two-body scattering. And in our case, two-body scattering simply means that you pick up a phase, which is L times pi. And I guess I forgot to write my pi here. There is a pi, that kind of pi, right? And so you say that if you want now this full wave function to be periodic, if you follow the coordinate of one particle all the way around the circle until it comes to the same point, it will have to jump over every other particle, so the wave function will pick up that much phase, and then of course it will pick up the phase of going around, the periodicity phase, so to speak, going around the circle. So that gives you this condition that the total phase picked up by each coordinate going around the circle should be a multiple of 2 pi. So this is the kinematical phase picked up if the momentum is k, 2 pi, the radius of the circle is 1, so I'm going around a circle of circumference 2 pi. So that's the dynamical phase picked up by the wave function, the exponential e to the I kx. This is the scattering phase picked up by all the remaining particles, and these are some integers that should be 0 or an integer, and these are some integers that in principle can be different for different particles. And that equation, or rather those n equations solved for the n ki, can produce the spectrum of the model, because the energy by assumption is the sum of these asymptotic momenta ki squared. This is the asymptotic bethe ansatz equation. You have, of course, to specify what these numbers should be. The easiest way to do it is to take the limit L going to 0 and then work by continuity. When L going to 0, and you know that if you have particles with momenta k1, k2, kn, you know that if the momenta are ordered like that, then these numbers should also be ordered like that. And that same selection rule, if you wish, you continue using when L increases, and therefore you find out that your energy eigenstates and eigenvalues are fixed in terms of these n integer quantum numbers. The solution for the momenta for the Calogero model is like that, and the energy is, of course, the asymptotic energy 1 sum ki squared. This is what we had found before. This for the Sutherland model, Sutherland because we are on a periodic space. These KR we call their pseudo-momenta. We call them pseudo-momenta because at no point of space is the wave function truly exponential in terms of this case. But in terms of those pseudo-momenta that depend on these quantum numbers like that, the energy assumes this free form. These pseudo-momenta, however, obey an expanded selection rule, because if the ni's are different and bigger or equal to each other in that form, the ki's will have to differ by L. So the bottom line is that the spectrum of the degeneracy of this system, the Calogero model with exchange interactions and distinguishable particles, is exactly the same as that for free particles. This ni would be the quantum numbers or momenta of corresponding free particles, just shifted in energy. So the degeneracy of these states is fixed by how many ways can you permute your distinguishable particles in that state. If you don't have fully distinguishable particles, but you have particles with internal degrees of freedom, the degeneracies will still be determined by in how many ways you can distribute these internal degrees of freedom among the states fixed by quantum numbers and I. So let's focus our attention on the model where the particles are in the ferromagnetic domain. That means they are bosons, and they have a spin SUQ. And we want to find the energy eigenstates of that spin-Calogero model and its eigenvalues. What you do is that you solve the free model, you renormalize the energies, and here renormalization simply meaning, for the harmonic model, simply means adding a ground state energy that is proportional to n squared. And then you distribute your particles in this single particle energy level. So what I'm writing here is to say that if these are the n quantum numbers for a single particle, when you have spin-Calogero particles, you do exactly the same as you would do for free particles. They are bosons, remember? So you can put as many of them as you wish in each state. So you can put them like this, say. But you have to take into account that they carry spin as you Q spin. When you put two bosonic particles on the same single particle state, the spins must necessarily be in a symmetric state. Therefore, if each particle has a spin in the fundamental representation, think of it as spin half if you wish for SU2, then this would be a spin in the doubly symmetric, singlet, fundamental, and then triply symmetric. And the full representation content in terms of the total SUQ global group would be, of course, the direct product of those representations. That's exactly what you would for a free system. That's exactly what you do now. Just take care of the fact that the energy has been shifted like that. And this is what this line means, that the total energy, if you go to the Sutherland model, in this case, the total energy will be given by these pseudo-momenta squared. The pseudo-momenta are like that. They are determined by these numbers Ni, these numbers N are this. And I guess it wasn't quite right for me to draw them starting from 0 and going up, because these Ni's now can be both positive and negative. They are like discrete momenta on the circle, but that's okay. And D, capital D, is the degeneracy, which is simply the dimensionality of the full representation that you have here. It also works for the spin-Calogero model, where in principle we shouldn't have any asymptotic bethe ansatz because there is no asymptotic condition, but the lesson learned from the asymptotic bethe ansatz works well there, and you can form the harmonic spin-Calogero states in exactly the same way. And that's nice, because now we can go places. And this will conclude my discussion about particle and spin models. It's the so-called freezing trick. Since we know that the Sutherland model, let me just show you. This model, I guess I haven't written, but sine square interaction here. That's what we are talking about. This model is completely solvable. And it has, well, a new spectrum, but degeneracy is exactly as in the free case. Now we say that we can solve it for any coupling constant L. So why don't we take the coupling constant L going to infinity? And just so that I don't keep pointing at stuff, it's L times L minus or plus Si dot Sj, roughly speaking, plus 1 over Q over sine square Xi minus Xj. What does it take the coupling constant L to infinity? Well, L, you see, L square is essentially the scale of the interaction, so the strength of the interaction becomes very, very strong. We want to see what are the low-lying states of this model. As it turns out, the low-lying states, because the interaction is very, very strong, will be either vibrational modes around the classical equilibrium point, because when the interaction becomes strong, it costs a lot of energy to deviate from the equilibrium point. So the vibrational modes, the phonons, will be one set of interactions, but also spin flippings, etc., will be part of the low energy spectrum. Let's call them spinons. And again, it's easy to see that the two are of the same magnitude. So the low-lying spectrum will contain excitations both from vibrational degrees of freedom and spin degrees of freedom. However, something else which is interesting happens. Because this interaction is very strong, the vibrations of the atoms around their equilibrium point will be very small. So the quantum fluctuations of this 1 over sine square Xi minus Xj will be very, very small. But the coupling of the spin degrees of freedom, this, to the coordinate degrees of freedom is simply through this term. S is here, the x's are there, that's the only term that couples spins and coordinates. And when the fluctuation of coordinates goes to 0, this becomes a classical term. Therefore, in that limit, spins and coordinate degrees of freedom decouple. Therefore, the full spectrum of the model will be the direct sum, or the product of the Hilbert spaces and spectra, of a spinless Sutherland model with a very large L, and a spin system, a spin chain system, where the particles here, where the coupling constant is this 1 over sine square potential, but for the values of the coordinates equal to the classical equilibrium point. Now, if you have a set of n particles on the circle repelling each other with symmetric interactions, and you drive these interactions to infinity to be very big, where will the classical ground state configuration be? It's obvious that it will be when the particles are equidistant on the circle, they form a regular lattice. So, that problem with the vibrations around the lattice is the Sutherland model, and the spins at that lattice, at those lattice points, interacting through inverse square interactions with the lattice chord distance, is the spin model. And that spin model, the spectrum of that spin model, can be deduced from the spectrum of the full model by moding up, if you wish. You can divide the partition functions of the spectrum of the Sutherland model. That spin model, which I write here for the 2 signs of interaction, was known before this method was devised. And it's called the Haldane-Shastri model. It was introduced, I believe, in 1988 or so by Duncan Haldane and Sriram Shastri, independently and almost at the same time. They solved it not through any of these methods. They solved it basically by identifying the ground state and then working their way from there. But using this method, it can be solved very easily, and you can find the states, the energies, and also the degeneracies or spin content quite easily. Moreover, you can play exactly the same game for the harmonic spin-Calogero model. That means inverse square interactions in a harmonic trap. Same thing happens. Particles freeze around their equilibrium and they just vibrate. And those equilibrium positions are the ones that minimize the potential, which is, I haven't written the potential, is the external potential, 1/2 omega squared xi squared sum. That's the trap potential, plus the relative potential, L times L minus 1 over xi minus xj potential square. This potential where I have rescaled this omega to scale like L square. Otherwise, when you drive L to infinity, this would become irrelevant. So you need to scale omega together with L. At that limit, in which case I can simply eliminate everything and pull an L square out. The minimum of that potential is found by differentiating with respect to xi. This is the classical equilibrium equation. And those minima actually are the same as the solutions of this equation. This is like a Bogomolny form of that equation. You want to see why it holds. You take each one of these terms and square it. You work a little bit and you see that you recover this potential plus a constant. So if all these terms are 0, because now the potential is the sum of positive definite quantities, that means that you are at the minimum of the potential which satisfies this. So you get a new spin chain model in which the spins are fixed at an inhomogeneous lattice that represents the zeros of the nth Hermite polynomial, because this equation is exactly what the zeros represent. And they interact through inverse square ferromagnetic or anti-ferromagnetic interactions that depends on their inverse distance. If you were given this spin chain at face value without any context and background, you would say, this is crazy, how can I solve this? Yet we know that it can be solved, and we did solve it that way. It has very nice properties. I believe this is the spin chain model that Karl-Jan Schoutens was talking last week. It has a very nice spectrum. Its spectrum of excitations is equidistant and with some corresponding spin content. And if you take the large n limit, the antiferromagnetic end, the ferromagnetic end becomes a ferromagnet, but the antiferromagnetic end becomes a conformal field theory with C equal 1. Exactly. There are no 1 over n corrections. There are various other generalizations of this trick for other spin chains. You can produce an SUPQ supersymmetric spin chain and so on and so forth, but you get the idea. So we are done essentially with the particle system and the exchange formulation and spin chain models. Let me summarize what we obtained out of that formulation. From this operator formulation, we found, first of all, a new, neat way to treat with the system in a way that we can not only diagonalize it, but also introduced spins practically from free, and then deducing the spectra of spin chain models that are distilled through this process. It was important that the coupling constant of the model L could be chosen at will, and it kind of makes the correspondence to free particles in generalized statistics more clear or motivated. On the other hand, the matrix formulation that we had before gave us arbitrary size spin representations. Remember, I stressed that although you can have any spin group SUQ that you want, you can only have the fundamental representation. You cannot assume that your elementary spins are in any higher representation. For instance, if we are talking about ordinary spins, SU2, you cannot have spin 1, you must have spin half. The matrix formulation, on the other hand, was giving us similar Calogero spin models where the spin could be in an arbitrary representation. Still symmetric, but not necessarily fundamental. The individual spins could be spin 1, spin 3/2, etc. On the other hand, we had no control of, I'm sorry, where am I? Here. We had no control of the coupling constant. This L here was fixed by everything else and could not be scaled. So we see that no formulation gives us everything. The matrix formulation gives one domain of models. The exchange operator formulation gives another domain of models. They have an overlap, but clearly none of them is perfect. And we would like to have a formulation that has the virtues of both arbitrary spin size, not just fundamental, and arbitrary coupling constant, so that we can play our freezing trick and derive spin chain models. And in particular, the point of interest would be with antiferromagnetic interactions and higher spin, spin 1. There is this famous Haldane conjecture that if you have antiferromagnetic interactions for integer spins, spin 1, etc., then the spin chain in the large number of spin limit develops a mass gap. That would be a way to validate or disprove that conjecture. I don't say prove, because it would be an explicit validation in yet one more case. This is still an open question. Do you have any questions up to that point? Splendid. Oh, there is a question. SU2, you mean the deformed SU2? I don't know how to deal with that. It can partially be dealt with, although not fully the way that I would like, in a chapter that I omitted altogether, the so-called foldings of the model. You start with the initial Calogero model, then you start folding it according to symmetries, and that gives you various generalizations. And there you do see things like anisotropic interactions that would correspond to SUQ. However, I don't know how it works in full, and I decided to omit this whole chapter because we wouldn't have time for anything else. Right.
Any other questions, comments? So I have a question about the last comment. So,
go ahead, yes.
So I guess the Hamiltonian for the spin 1 case would be like, it's not like a Heisenberg interaction, S.S interaction. You must have some additional terms, right?
Look, if it is a Heisenberg interaction, then it's not solvable. You can add higher order terms. But see what's happening. If you add higher order terms in a way that make it solvable, what you're doing is essentially you're encoding SU3 dynamics in the spin 1 representation of SU2. So you can choose to to view it as an SU2 model with a nonlinear interaction, but what it's really, it has a hidden symmetry, which is SU3, and in SU3 it becomes an exchange spin interaction. I would like something that is strictly of the Heisenberg type with higher spins, because that's where the theorem of the Haldane mass gap theorem would apply. It is open problem, yes. Good. Oh, sorry, no time for that. I had decided, so let's move on. Let's change gears now and move to hydrodynamics so that we can talk about the continuum limit of the system and make contact with talks by Sasha before. In all particle systems that we do not have coalescence where they form tight bound states, etc., we can take the fluid mechanical limit. I will call it the hydrodynamic limit, although it's a slight abuse of language. These are really fluids, and sometimes they look more like gases than actual liquids, but let's call it hydro anyway. This is a limit that should become exact in the n equal infinity, the number of particles go to infinity, although in many instances, and in this particular one, you can add terms that take into account finite n effects and make the description even more accurate, even looking at the coarse graining of particles. And in this particular case, for the Calogero model, since the original particle system is integrable, you expect to end up with an integrable fluid mechanical model. One way, perhaps the most obvious way to deal with the transition from particles to fluids is the Lagrange approach. Not the Lagrangian, but the approach used by Lagrange. And sometimes we call it the body fixed or particle fixed approach. You can order the particle coordinates in a particular way. They don't have to remain in that ordering. They can then start going over each other, and that would mean that your fluid description would develop caustics or shock waves, and you've heard a little bit about them. But in our case, we are lucky because when you have Calogero particles, I'm talking about the classical Calogero model now, they never go through each other. And then turn that index J that labels the particles in order as they come on the real line, promote it into a continuous variable. The assumption being that if the particles are many, the change from particle J to J plus 1 is very small, so that J, perhaps rescaled over n, becomes a continuous variable that parameterizes positions and velocities, etc. So the position of the particle would become a function of time, of course, but also this sigma that plays the role of J, and it should be a smooth function of sigma in the hydrodynamic limit. The fluid density, of course, is the inverse of the distance between two nearby particles, and all that in the continuous language is expressed in this way. It's the derivative of x with respect to sigma to the minus 1, and the velocity is simply the velocity field is simply the velocity of particle x with respect to t, so it's dx over dt parameterized like that. The equations of motion, again, are very easy to find because they are essentially Newton's equation for particle at position x. Remember this, at position sigma, I'm sorry. Remember that this sigma follows the particle. So it's simply that the acceleration equals the force, and that force on particle j that we call sigma, in general depends on the full x of sigma because the particle interacts with the remaining particles. That's one description, and you can go some way actually using that description. The other description is the Euler description, and here thanks Sasha for doing all the background work in explaining how this works, so I will go fast. In that description, we are not interested to follow the particles as they go around. We just want to look at them and see only a density and a velocity field. So those should be our dynamical variables. We can reformulate our equations of motion in terms of those variables, and we'll have the continuity equation expressing the fact that particles are conserved, and the Euler equation, that's the body fixed derivatives of V, and that's the force, which is simply Newton's law for a fluid particle, which could mean not necessarily on an individual particle, but a very small volume of fluid. This equation did not exist in the Lagrange formulation because it was an identity. It was a trivial identity, like 1 equal to 1. Here we have to include it as an extra dynamical equation. The nice thing about the Euler description is that it is Hamiltonian. You can endow the density and velocity fields with Poisson brackets, classical Poisson brackets of this form. This, in the quantum version, is called a Abelian current algebra, but it is what it is here. And you can write a Hamiltonian that upon Poisson brackets would reproduce those equations of motion. And that Hamiltonian is always of the form kinetic plus potential energy. The kinetic energy is just 1/2 mv squared, which turns out to be this, integrated over all positions x. And the whole point now is to figure out what the potential energy is as a function or a functional of the density of the particles. You see already that if you take the Poisson bracket of rho with h, the only place that does not commute in the Poisson sense with rho is here, this v squared, because this is only a function of rho. So that immediately gives you the continuity equation. That v with h will give you that equation. So we need to figure out that potential energy. You say it should be enough to write the many-body potential energy and rewrite it, turn it into an expression in terms of those densities and velocities. If we have an external potential, call it V0 of x, like a trap, and an interaction, a two-body interaction potential V of x minus y, x and y being the positions of two particles, we would expect that interaction energy to be the integral of density over V0 x, which simply counts this rho of x, this density of particles at position x, counts the energy of these particles and sums over all of them. And you would expect the interaction energy to be of this form. Rho x dx and rho y dy are the number of particles in a small region dx and dy around positions x and y. Those particles at those positions interact with this potential, so that should be their interaction energy, and you sum over all positions, maybe with a factor of 1/2 here if you don't want to overcount, and that should be your total potential energy. This is always the correct answer. The second part, however, is not always so, and we will spend some little bit of time justifying why not so. The continuum formula, that one, for the two-body interaction is only valid if near neighbor, not necessarily nearest, but near neighbor particles, few neighbor particles, do not contribute a macroscopic fraction of the potential. Because in the continuous expression, you assume that everything happens when you take these particles here and there as if they are always far away, and that will give you the full contribution. What if, when these regions go near each other, their contribution increases so that the contribution from a small region around them becomes a sizable fraction of the total? Let's see when that would happen. Assume that v of x minus y has a power law at coincidence points. I don't know what happens when they're far away. I'm interested to see what happens when x goes close to y. So assume that it has this power law, and I would like to see what is the contribution of particles nearby to the total potential. Well, the total potential U would be the sum of I minus J. Let's say that particles in that region are a distance A away from each other. So I and J, A times I and A times J are their positions. So you would need to take that behavior and sum it for all I different than J. Actually, because this depends only for the difference, we can fix I and sum later, and just sum over J, which are the particles around this particle I. And this difference I minus J I call K. So this would be the sum of K to the gamma, where K is the distance between those, to the power gamma, and only positive powers because this is an absolute value. If this sum here is finite, it means that the first several, but finite number of neighbors of I will contribute a finite amount. If this sum here is infinite, it means that no finite chunk of it will contribute a substantial amount, and therefore the continuous expression will be correct. But of course, this sum is, as we know, is finite when this exponent gamma will be infinite if this exponent gamma is bigger than or equal actually to -1, and it will be finite if gamma is less than -1. So if the interaction falls off faster than 1 over r, this sum will be finite. If it falls slower than 1 over r, it will be infinite. So for a behavior where the potential falls off slower than 1 over r, we know that the continuum formula will be correct. But for interactions stronger than that, stronger than 1 over r at coincident points, the continuum formula fails. The Calogero is inside that region, is gamma equal -2. The sum is finite, and therefore we cannot use the continuum formula, and we need to have a more careful analysis. Here is an exercise to take home, if you wish. Consider particles interacting with nearest neighbor harmonic potentials of this form. So that's the interaction of those particles. Derive the Euler description of the fluid system according to what I told you. This is a sum of harmonic oscillators. It's not permutation symmetric, but it's still harmonic oscillators. So it's obviously solvable and integrable. Therefore, the fluid mechanical system must be 2, although it won't be obvious by the form that you get. Nevertheless, try and derive the conserved integrals of that fluid mechanical system, knowing that this is an integrable. And by the way, this is a known case, which is called the Chaplygin gas. It's integrable in 1 dimension. You can extend it to more than 1 dimension, in which case it's not integrable, and it has some interesting applications in cosmology. Yes?
In the continuum, the integral is like dx dy, x minus y mod gamma. So there are 2 measure factors, dx and dy. So if I have rho x and rho y as some smooth quantity, and if I replace 1 over x minus, if I use v equal to 1 over x minus y mod square, right, then of course there's a problem. But anything like 1 over x minus y to the power 1.5, that should have been okay.
Let's assume that this goes like 1 over absolute value x minus y. It's still a function of the difference. So you can decide to do the integrations 1 by 1. First over x, then over y. When you do this integral, say, over x first, you are ending up integrating over this variable, change in variable, multiplied by some smooth functions of x and y. Integral of 1 over x is infinite.
No, but then, okay, so, but if I use polar coordinates, r dr d theta,
yeah,
and I have r dr divided by r, so that's fine.
That is not r, that's absolute value of x minus y. It's not the two-dimensional, it's not a two-dimensional space that r is the radius. This is the absolute value of real coordinate x minus real coordinate y, and you integrate over them. You do that. That's exactly what I did. So the center of mass coordinate has no problem. The relative coordinate would still be an integral of 1 over x dx.
I see.
So you could see it from here. But I wanted to show you what's the origin of that thing. It's not that something horrible happens with this system. It's just that this is trying to tell you you are neglecting a very important part of the contribution, which comes from the nearest neighbors that are not described well in this continuum limit. Okay. So, yes.
Gamma is greater than -1, then I can just blindly write the continuum, right, with no problems?
No problems.
For any arbitrary shape?
As long as the interaction does not blow up faster than 1 over r, so it's 1 over r to the half or something like that, you're fine.
Okay, yeah.
In particular, this one is entirely regular. That's why I gave it as an exercise. I didn't want you to go through any. It's just fun to do, that's all. Is that surprising for any reason, or contrary to something that you knew? Because you seem surprised. Right. You can use this, where this would be v of x comma y. The only thing you want is when x goes close to y, how the potential should behave. If it doesn't blow up too badly, you can use that formula. Okay, so for the Calogero model, like in many other instances in physics, quantum mechanics preceded classical mechanics. It was actually easier in some sense to solve the problem of how to write this potential quantum mechanically than classically. And that goes under the name collective field method, or collective field theory sometime method, developed by Sakita and his student Yevitsky, and I guess also Das. Sakita, Yevitsky, Dar, I think. The motivation for doing it was that they wanted to actually deal with matrix models, but the method works more generally. And the idea is that when you have your quantum mechanical problem, a little bit in the spirit of what I told you in lecture 1, when you have quantum mechanical problem, you want to reformulate your Schrödinger equation, let's call it, the evolution equation, in terms of singlet variables or in terms of collective variables, variables that describe the collective behavior of the system. For the matrix model, it would be the traces of m to the n. And for particle models, it would be these I and m quantities that I told you before. When you do that, it's like a big, horrible-looking change of variables, but you can do it, and you need to take into account the fact that when you change variables, your measure changes. So when you write your equation, you have to put the right measure factors to have hermiticity, but all that can be done. It was done for the free fermion case, for instance, by Cevicki, I think. And it can also be done by Calogero. I believe it was done by Andrich and by Cevicki, Andrich and Levine, I think, and then Andrich, Cevicki, Bardek, sorry, yes. Yes, but that was done, I don't know, 20 or more years ago. And the way to do it is that because of this singular form of interactions, you write your wave function as this factor, which kind of takes into account of the behavior of the wave function coincident points times the rest. And then you perform your procedure for that wave function phi. I will not do it for you. It's complicated and not the point. You find that the potential that you have to put in your medi-body Calogero model, some kind of functional equation for rho and v, should be this one. Now, this rho h, we've seen it before. It is the Hilbert transform of rho. And you see that it contains this term that depends on L squared, this term that is L times L minus 1, and this term which is L minus 1 squared. This term is cubic in rho. This is quadratic in rho. And this term is linear in rho, I mean under scaling. It's not a linear function, but it's linear under scaling of rho. So because rho, integral of rho is the number of particles n, rho scales like the number of particles for a system of finite size. So these are different powers in n. This is the leading behavior, n to the cube. This is subleading, and this is sub-subleading. But there are no other terms here. So let's look at it for a while. First of all, this was derived quantum mechanically, but we can easily take the classical limit. Remember that in the classical limit, L becomes big, and this minus 1 here is essentially h bar. So in the classical limit, all these three coefficients simply become L squared, equal to the coupling constant of the Calogero model. The term rho cube being the leading term is exactly the same as what you would have for non-interacting fermions. The only difference is that the coefficient has been renormalized to I squared L squared. This L would be 1 for fermions. So you already see here a kind of behavior of this system as almost like free fermions in a large n limit, but with a rescaled Fermi momentum, because that coefficient here determines the Fermi momentum. This first subleading term here would be the naive potential, because rho h, right here, rho h is like integral of rho y x minus y, depending whether you're doing it on the line, etc., dy. So when you take the derivative of this, it becomes this, up to a minus sign. And when you multiply by rho, you can introduce rho x here. So you see it's rho x, rho y over x minus y squared. This is exactly the naive expression you would write for two particles. Only here it is regularized appropriately, because without this derivative and this rho, this is the principal value. And when you take the second derivative, you have to take into account of that principal value to see what you get. So this, you could consider it as a regularized version of the naive expression. And that is a subleading correction, subleading in n, and subleading also in derivatives, because it has an extra derivative. You see, this has no derivatives, one derivative, two derivatives. All right. All this is fine, and we can say, thank you, quantum mechanics, we will take it and run with it, and that's what we did for a while. But it would be nice to see that we can derive this result classically. Here I will give you basically the calculation as was done by Michael Stone and his students. Sasha gave you an alternative way that I will comment on it later on. But here I would like kind of honestly take the classical system and derive that expression by taking the limit of the particles going to infinity. The basic identity that I will use anyway, it wasn't quite done like that by Stone, but we did it like that with Manas when we revisited that problem, was to take this identity over all functions, or smooth enough functions, if you wish. The sum, actually this is true for all functions as long as the Fourier transform can be defined. The sum of the values of functions for all the integers is the sum of the Fourier transform of the functions for all the integer multiples of pi. It's an identity that you can easily prove. This relation is important, and it appears in various guises. It's in the root of many of the dualities that people talk in string theory and other parts of physics. Also, it's the root behind some formulations of bosonization. And it also appears in instanton expansions when you write a path integral as the Gaussian fluctuations around the equilibrium point, but then you have to sum overall classical minimum of the action. That's exactly that type of sum. Now, we will assume that our function f is smooth at the scale of 1, because this n here, this value will become like our sigma, the particle variable that in integer values would be I, 1, 2, 3, etc. So you would like this function to be smooth at scale 1. You could rescale everything to make that be 1 over n. And for such smooth functions, you know that the Fourier transform will be dominated by the term n equals 0, and all the higher terms will be highly suppressed. Therefore, for such smooth functions, you say that in this sum to the right-hand side, only the 0 momentum, n equals 0, will contribute, which is simply the integral. So this is just a lot of words to tell you that you can approximate the sum of a function over the integers by its integral. This just sets the rules of when that sum will be well approximated by that, and what type of deviations you expect. As I will argue, any deviations from this relation when this represents the particle number will be non-perturbative in the number of particles. So this expression for the hydrodynamic limit is perturbatively exact. Let's do it quickly. I don't want to spend too much time, but let's consider the contribution to the Calogero potential from the particles around a particle x0. Just pick any particle in your system x0 and say, let me see, this particle, how much does it contribute to the potential? Well, you have to sum its distance, inverse distance squares from all the other particles and see what that is. And I put here a factor of 1/2, because if you then want to add over all those, you're overcounting. But that's basically what you need to calculate. If you know how to correctly calculate that, then you can sum over all the particles and you're done. And in the continuum description, that will be 1 over x of 0 minus x of n. This becomes simply variables. Because this is not a smooth function of s, we cannot use the formula that I told you before. The trick is to define a regularized function f of s. Now, I want to make an important point here. It's not that I will do a particular regularization and that regularization will give me an answer, so I have to suspect that this answer will be regularization dependent. I claim that I will find an answer which is unique, and the way to do it is that I will consider another function, call it f of s, which is like a regular expression of this. And I don't claim yet how the two are related. All I say is, consider this function. It's a function that is exactly what I would need to add here, minus those two terms that have the property that as s goes to 0, the total function becomes completely regular. This term cancels the second order pole, and this term, the first order pole, I added an S cube thing because I wanted the sum of this term to be finite for technical reasons. All I say is, look at this function. It's a smooth function, it has continuous derivatives everywhere, and it's finite with continuous derivatives. It's a smooth in the scale of 1, and therefore for that function, I can apply my basic identity. The left-hand side will be the sum of this function at integer points. That is f of 0 plus f for other integers not equal to 0. F of 0 is this value. And the sum for f different than 0, look at it, it's the sum of this term here, which is my potential, maybe times 2 because of that overcounting. But I also have to sum these terms. This term sums to 0 because it's odd, that is symmetric under S and integrable. This term, however, does not sum to 0. It gives a well-known contribution, which is pi squared over 3. Okay? Therefore, this is the exact expression for the sum of the values of f of s. Now I have to find the integral of this function over all s. That integral, I don't give the details here, is like the integral of this, where am I? Here. It's like the integral of this function, which doesn't exist, plus some regulator terms. By regulator terms, I mean it's not that integral, it's the integral of this function, which can be seen as that integral with extra terms. In fact, just to put a little bit more meat in these quotation marks here, missing steps, is because this function is smooth and regular everywhere, you can perform that integral by excising a small finite region, a small infinitesimal region around the origin. So you can do the integral over all s except a region minus epsilon plus epsilon in the origin. I miss nothing because, where am I? Yeah. I miss nothing because this is a smooth function, so this contribution will be infinitesimal. When I do that, I find out, and I write it out, taking into account these terms, I find out that what I obtain is something like the regularization of the derivative, is a regularized form of the derivative of the Hilbert transform, plus things that go to 0. So I claim that if you integrate that function over all s, you will find exactly this answer. This is not an approximation. This is an exact result when this rho 0h is that.
Excuse me, so
Yes.
is the epsilon in the second equation
sorry,
the regularization term?
No, mea culpa. It's a different epsilon. This epsilon is a technical thing that I needed to make this function such that this term has a finite sum over all s. Because sum of 1 over s, you could say it's 0, but it's not summable, so I want something that is both integrable, summable and to 0. So that's one epsilon. Here, call it delta. You integrate, and I claim, and I say that the region from minus delta to delta that I miss will go to 0, because this function f is smooth. But then this allows me to see what it is that I get when I integrate this, and it turns out to be exactly the derivative of the Hilbert transform. So everything together, I can use that, I can use this result and put it there, and which expresses the sum of this, the potential in terms of the Hilbert transform overall, plus these other functions that I have here that contain double derivative of x of 0 and triple derivative and single derivative, etc. But all these derivatives can be turned into potential in its derivatives because d over ds, d over the particle number is 1 over rho d over
Excuse
dx.
me? So I have one question. So this, can you go back to the previous page?
I'm sorry?
So can you go back to the previous?
Yes, of course.
So this derivative looks something like Schwarzschild derivative, and is there any connection? The second.
Oh, you mean this one?
Yeah.
Is it called the... yeah.
Maybe coefficients are different, but something looks like Schwarzschild.
It would be an interesting observation if something can be done of this, yes. All I know, is that this is what you need to add. You could add other terms too, but this is what you need to add to make this function smooth, because this function is not smooth, you add stuff to make it smooth. You may say, well, how do I know that what you found does not depend on R? I claim that I did an honest calculation, and that is what I get. So I didn't cheat, and I found that this sum has to be expressed like that. But let's say that you added here a function that was different than this one. Well, if it was a different function, it still gave you the same smooth f of x. That means that it would differ by this function by some regular term. So I assume that f of s is this plus a regular function g of sigma. You can do exactly the same thing. On the left-hand side, you would find what we found here plus the sum of g of n. So if I have plus g of sigma, on the left-hand side, I had the extra sum g of n. I would have this extra sum. And on the right-hand side, when I do this integral, and I would have an extra term, which would be integral of g of sigma, g sigma. However, if g is a small function, I know that the sum over g of n is equal to the integral of g of sigma up to non-perturbative terms. Therefore, these two terms would drop from the result, and I would recover the same result. This is just stressing the point that this result is unique and not regularization dependent. Well, you turn S into X and rho using this way, so all these derivatives and higher derivatives can be expressed, and lo and behold, your V0 here, V0 was the contribution of particle X0 to the potential. It's exactly this term. So the total potential will be the sum of these contributions for all particles. Now I can multiply by rho of x0 and integrate. So I just put an extra rho here, and I recover exactly the result of quantum mechanics. For, with the coefficient here, GL square, all these coefficients here are the same. I stress that this result is perturbatively exact. There are no other terms here. The higher Fourier modes would contribute terms that would grow like, that would behave like e to the minus n. They are exponential in n, the number of particles. Therefore, non-perturbative in 1 over n. And they are not important. They are only important when they do become big, and that's only when we have effects like depletion, when the distribution of particles breaks into 2 or more components. In this particular case also, we have no gradient catastrophe. This, I remind you, is what Sasha told you, that for the free fermion case, you can have particles overtaking each other, and that leads to shock waves or caustics. That is called the gradient catastrophe. Here, the subleading terms fully regulate rho cube, so the equation of motion for the fluid that you get from here has no such effects. And for the trigonometric or hyperbolic potential, you just change your definition of Hilbert transform here. It amounts to making the system periodic in X. Okay. Yes.
If you go back, so is there any subtlety in just introducing, including the Weierstrass function here? I mean, that should also work, right? If the kernel is a zeta function, then is that the collective field theory of the Weierstrass-Calogero model?
It should be, except as you know that when you sum the 1 over sinh square thing, you find something that is not quite periodic. It needs to be regularized. We went through that with some linear terms, but in principle, yes.
No, but if you go by the procedure that you explained, then...
if I go through the procedure,
yeah.
Yes, you should probably get something like generalized H here, but one should do it and go carefully and see what you get. You would need to sum things, to calculate some finite sums involving the Weierstrass function, not finite sums, sums that are finite, like this. Let me see. You need to sum over this term here. That sums to 0. You need to sum over this term, and that can be done and gives you that. You need to sum over similar terms involving the Weierstrass function.
Right, okay.
I have also a question, comment. The last term is dx rho squared divided by 8 rho. It's like a modelung pressure term in
Right. Some people call it the entropy term or some, but
Yeah.
yes, it's a modeling, right.
So which means that if you encode like square root of rho times e to the I theta as a complex field where
Right,
theta is
right,
gradient
exactly.
theta is velocity fields, and it's this term is disappears. It's implicit there.
Exactly.
So can it simplify the derivations? That's the question.
I don't know that it can simplify. Let me expand on what Sasha said. If you take just ordinary quantum mechanics and you say, I don't like my wave function, I would prefer to have the modulus and the phase of the wave function as arguments, then you rewrite your Schrödinger equation, and this term appears here. This rho is actually the modulus of the wave function. And when you turn that into a field theory, the absolute value of the wave function squared, actually, becomes the density of particles. So it's a very natural term, and it exists if you do the same thing, either this way or rather quantum mechanically with the collective field method, you would recover the hydrodynamics of three bosons. What you would recover, I need to go back to the quantum expression, is L equals 0. So this term drops, only that term refers. And that's exactly the Madelung term that Sasha pointed out. So this is what you would have for free bosons. This is what you would have for free fermions. And for Calogero particles, you have both and the term in between. Yeah, right. So it's very suggestive, but I don't know how to use the fact that it comes from Schrödinger equation to simplify this derivation. Let me, yeah. Yeah, absolutely. Yes. Presumably. I'm not inclined to say yes, because I haven't done the calculation and the Weierstrass function has some peculiarities. One needs to sit down and do it. But it's a good guess that you would recover terms like that. Right. So, yeah. So let's go quickly over this field theory. The equations of motion that you get from what we just derived, classical, is always the continuity equation and the dynamical evolution for the velocity field, which has this form. Say again? Okay. Which looks like that. We can look for small amplitude waves. That means we can linearize these equations over a classical solution representing a background of constant density. You fill your space with particles, and at equilibrium, of course, the density is going to be constant. And you do it. It's easy. It's linearization of this equation. And you found that these small amplitude waves will have a dispersion relation like that. It's a nonlinear dispersion that has a linear part and a quadratic part like that. The velocity of sound defined as the velocity derived, the group velocity derived for phase from this relation for small wave number, for large wavelengths, turns out to be this. And in terms of the group velocity, this dispersion relation acquires this form. So I wrote it in this way to stress that sound waves, which are these waves, only travel at velocities less than the velocity of sound. In the limit of very large wavelengths, they travel with the velocity of sound, but for any wavelength shorter than, for any finite wavelength, their speed is less than the velocity of sound. They cannot travel higher. Also, I noticed that in this expression for omega has the property that the value for k and the value for 2 pi rho minus k are the same. This is nothing but Umklapp, because when k becomes of the order of pi rho, that means that the wavelength of this excitation is of the order of the distance of the particles. So, of course, such waves are invisible, and it's like going back to 0. You can also find solitons, as Sasha has told you. You can write a soliton or finite wave by choosing your solution to be of that form, and you find that you do have a rational type of solitons. This is rho 0 plus something else, and this something else away from the center of the soliton put at 0 drops like 1 over x squared. And the details are not important, but a couple of things are of interest. The speed of those solitons from their form can only be bigger than the speed of sound. So, although small amplitude waves can travel with speeds less than sound, these can travel only with speeds bigger than the speed of sound. And as the speed of the solitons becomes very big, they become very highly picked. They become like delta functions. As the speed of the solitons approaches the speed of sound, they become very broad, and eventually they disappear, they dilute into the continuum, if you wish. You can calculate the particle number carried by these solitons, the excess integral of rho over rho 0, and the momentum of these solitons, and the energy of these solitons, and they have these simple forms. So they are exactly the same as if you had Q equal 1, one particle at velocity of mass 1, at velocity v, and kinetic energy 1/2 mv squared. So solitons, for all purposes, behave like free particles at speed v. In the many-body description, solitons are like particles going through the system in a kind of neutron's cradle way. They bumped their previous particle, that continues, and so on and so forth. You can also find finite amplitude waves, and again, I'm running, okay, I'm not going to finish. All I wanted to stress here is that these finite particle waves do have a semi-classical description. Even though the system is classical, they do have a semi-classical description in terms of a pseudo-Fermi sea. Actually, it's a Latinger sea because they form a Latinger liquid. Even classically, you can describe your system in terms of a filled Fermi sea. The density of filling now is 1 over L as opposed to 1. Solitons correspond to peeling one particle out of here and putting it up here. So solitons are particle excitations. Small amplitude waves are like Hall excitations. It's like depleting this sea by a little bit and push this upper bound by what it needs so that the particle number be conserved. And these finite amplitude waves are like finite gaps inside this pseudo Dirac sea, this Latinger sea, if you wish. So it's quite interesting that the classical model has a full description in terms of this semi-classical, semi-quantum, we should say, in this case, quantities. And it's also another fact that soliton excitations are dual to particle excitations. You can take the limit of solitons and waves. You can take the limit of solitons and get sound waves, and you can take a coherent state of sound waves and they will form solitons. Now, Chair, how much time do I have? 3 minutes. It's not nearly enough. I wanted to explain in my way, my and Mana's way, the work of Sasha and Paul Wiegmann and Eldad, I guess, Bettelheim, because this quantum Calogero, this Calogero models, not quantum, these classical Calogero models have a dual formulation in terms of coordinates, and some dual coordinates that are not their momenta, they are something else, they represent solitons. But I'm afraid that the time will not be enough to do that. So let's see what it makes sense to. Well, I'll just describe it because the equations that Sasha and his collaborators wrote seemed to us a little bit magical. We didn't know where they came from. We decided to see if we can derive them using kind of a canonical, in quotation marks, procedure. And our way of doing it is the following. Start from a set of first-order equations. These are not Hamiltonian. There are particles xa, I use the index a to run from 1 to n. And the equations of motion are that ma, think of it as a mass, times xa dot equal the derivative with respect to a of some function of these coordinates. Now, this is a first-order equation, but of course you can derive the second order by taking another time derivative and using this inside it. And these second-order equations take this suggested form. They become minus dv over dxa, exactly the Newtonian equations of motion, if you define as your potential that function. Then you go hunt. You say, I can choose any phi that I want here, but I don't like to end up with a system that has interactions that are 3-body, 4-body, etc. I would like to have a system that has only 1-body interactions, that means an external potential, my second order, and at most 2 bodies. Are we done? You want me to stop? No, good, thank you. So we do that, we go through some algebra, some procedure, we end up with a couple of functional equations that need to be imposed if you want to functions that define your potential if you want the result to be of the form that I told you. And here are the answers. This is the allowed two-body potentials. Surprise, surprise, they are all of the Calogero type. I didn't start with that, but that's where we ended. This is not a complete list, but this is because of interest. But you are also allowed to add external one-body potentials. These one-body potentials have these terms and the square of this function, so they can be quartic the potentials or trigonometric the potentials here. All this is fine and dandy, but can I go over like 1 minute or so? Okay, this is all fine, but you very soon realize that what you are doing is a little bit dumb because your potential is negative definite. So yes, you are describing a dynamical system this way, but it is unstable. You would like to stabilize it. And it turns out that the only way to stabilize it is to turn this potential into an imaginary potential that takes care of the sign. But in order to have real particles, you have to break them into a real set and a complex set. You see to what constraint that implies to the masses, and you find that the masses of all the real particles have to be equal, and all the complex particles have to be minus that equal value. And if you do that, then the real particles will remain real, and they will not become complex by interacting with these complex ones. And you end up with these dual equations, which are essentially the equations of Sasha and company here, written for a general potential, written from that list here, okay? The interesting thing is that they are complex, but their second order term gives you a real evolution for x, and that you can somehow view the solitons. These will be solitons because they are the guiding centers of soliton excitations, are as particles moving on the complex plane with negative mass. If you know the ZAs, you can actually recover the motion of the particles because from the reality of the x's, these two equations follow, and these are equations that, if solved, give you the x's, and these are equations that give you directly their velocity. So all this is fine, and it is as described by Sasha. How do you do hydrodynamics? Again, I will just describe it in words. You introduce one more, in our way, you introduce one more particle that we call it the spectator particle, that is there just to monitor the system. So you just put a particle, a spy particle extra there, and you say, you move along with the system and see what it does. This particle has to be like a pilot fish. It has to follow the system, but not influence it. And the way to do it is to drive the mass of this particle to zero. You do it, you find some equations of motion for the particle's velocity that we will call u, and then you say, good. Now that I've done that, I will sprinkle the system with a lot of such particles, like when you go to a stream and you sprinkle it with sawdust, and the motion of the sawdust will describe the motion of that fluid. You do it, you sprinkle particles at every position x, and therefore you promote this function, which was the velocity of that extra particle. You promote it into a function of x, which is the position that you place these particles, and you work through it, and lo and behold, that u, or actually this u broken into two parts, u plus and u minus, are the u1 and u2 that Sasha described to you before. So if you wish, all that was a repetition of what you had last week, kind of trying to motivate it from a way that at least there is a mental picture behind it, and explain or give a meaning to what these variables are. Well, then you can write it in the continuum limit. Sasha and operators wrote mysterious term right out of hand. It's still a little bit unclear, at least to me, how this works if this is a delta function. But that's okay, because this is the correct continuum limit, and you can show it using the regularization of u that we did before, so all is fine. And therefore, this is a good framework to describe both your particles, don't worry about that, both finite number of particles and hydrodynamic excitations, and that's what we did in a paper with Manas Kulkarni. This for particles, Calogero particles in a quartic potential that is still integrable, as we knew from previous work, but had no explicit solutions. But you see what happens. The external particles goes through the other particles. What happens is that it doesn't go through, it bumps other particles and then gets reflected, and the other particle assumes its velocity, and the whole system evolves. It's not periodic in time anymore, but lo and behold, this particle keeps going around like a soliton as it should, and this is a two-soliton solution, harder to see, but now there are two solitons. The thing is that it doesn't just mix into a total mess. The solitons remain well-defined and propagate in time, and never mind that. Good. Can I take 1 minute to say? You're a very kind chair, thank you. So what we did in those 3 lectures was a grand tour in Calogero land. We did leave out many things. I didn't tell you about leaf foldings and the interesting new systems that they produce. I didn't talk about the interesting topic of density correlations and their analytic challenges where Jack polynomials enter, etc. I didn't talk about the connection with two-dimensional Yang-Mills or three-dimensional Chern-Simons field theories. I didn't touch upon the relativistic Calogero model, sometimes called the Reisener-Schneider model. Relativistic in quotation marks, it's not quite relativistic. And I didn't expand on the duality in these models and their manifestations. Still, I want to stress that there are many open questions remaining, questions to which I, and I believe other people, don't know the answers. The first and foremost is what I already told you. We would like to have a more general formulation that encompasses both matrix and operator formulations. It's the superset of those formulations, so that we can do the tricks that I told you before. It seems to me that these 2 formulations individually are incomplete. It would be good to correlate density correlations for irrational values of L. Why? Because the only known cases in which such density correlations are calculated are those for which L is a rational number. Not only that, but if L is of the form P over Q, the result for the density-density correlation is in the form of an integral that is P plus Q plus 1 dimensional. That is, you need to perform P plus Q plus 1 integrals in some horrendous integrand to find that correlation value. But tell me, the difference between L equal 1 and L equal 1,000 over 1,001, do you expect that the correlation functions will differ dramatically? No, they wouldn't. Everything is continuous in L. Yet this expression would be just a double integral, while that expression would be an integral with 2002 variables. This is crazy. This means that this 2002 variables integration is equal almost to that other integration. So it cries for a better expression, for a different way of approaching the problem in which the form of the answer is continuous in L. The elliptic model is still full of challenges. Its full solution is missing and very little is known about it. Nothing at all is known about the non-commutative models that I didn't derive from you, but it derives from this folding thing. And lots of other questions persist. Use your imagination. I would like to stress that sometimes the fun is in the dark, unexplored corners of an old subject where the old hands in the field either didn't think of going or they went, but they were too wed to their own way of thinking and didn't see interesting new possibilities. So that's an invitation to those of you who would like to do it, that yes, this is an open field, and thank you for attending these lectures.
Comments? Any questions, comments?
I have just comment one thing which was, I think, missing in this story is that there is very interesting reduction of these equations. If you take this bidirectional Benjamin-Nona equation written in terms of rho and v, it turns out that it's possible to find some initial condition which relates rho and v in such a way that all these profiles of density and velocity move to only in one direction in a particular way.
Spiral motion,
it's chiral.
That was in your paper with Paul Wiegmann.
Paul and Eldad, yes.
And Eldad, okay.
So
yes.
nobody explored this system. Of course, if you expand in small deviations, it becomes just regular Calogero model, but it has some logarithm of density, so it's very interesting equation.
Yeah, I remember
it also
that
can be obtained
equation.
from this Calogero.
It was one of the things that fascinated me after you did that work.
It is very weird, and I think it's one of the unexplored parts as well.
My ambition or my dream would be to see a decomposition of the Benjamin-Ono equation into two clearly decoupling chiral factors. This is not quite what's happening with U plus U minus. I would like to say it more explicitly. It's obvious that it should be the case because when you write this description here, it's clear that there is this and that side. This is all the right moving excitations. Here you can have solitons, you can have finite waves, whatever, and the same thing you can have here. And as long as you are not exciting the system so that the two couple, which is a non-perturbative effect, you should be able to describe those and those separately. Yet I haven't seen yet an equation that makes that explicit and cleanly.
And I don't think it is possible, but what we showed is that it's possible to do projection on one side.
To have only this.
So you fine-tune the lower part so that the right part satisfies self-consistent equation.
Right, right.
That's
So you have this, I believe.
Yeah.
I would like to see this. You don't believe that it exists. I'm still an optimist.
And one more quick comment is that the case when multiple integrals becomes more or less identical to one, it's if you take x-axis spin chain and you ask for this emptiness formation probability, then exact formula is given in terms of the number of integrals given by the number of sites in this emptiness. And Lukyanov and others were able to do some saddle point analysis when the number of these integrals goes to infinity to extract quite simple answers. And this also corresponds to hydrodynamic calculation that we did. So somehow it's probably that the multiple integral part has a good description in hydrodynamics variables again. So
it is possible. I would like to see it. So that would be the limit of... by the way, you are already at the hydrodynamic limit here, because this is a density correlation with the number of particles goes to infinity. This is just expressions that you get in terms of the coupling constant, L. So I don't know if the limit of infinitely many integrals is a hydrodynamic limit. It's simply a limit of going to a rational number through rationals infinitesimally close to it.
I mean something more like one, that this 2002 integrals
yes.
is two integrals plus some dressing using hydrodynamic variables, something like that.
Could be, yeah. Okay.
Questions, comments? So if not, let's thank Alexios. Okay. So the time is slightly behind the schedule, so let's start the next talk from 11:35.